Hello class, this is CSE-5250, sections 2 and 60, week 3, well, this is going to be post week 4, spring 2026. Alright, so let's look at what we're going to be doing for Peter's assignment number 2. So this is 4 parts, so it is a bit more involved, but the additions you're doing are outlined in the slides, but I'm also going to demo them in this video. So, you are going to need your pi estimating program from the last assignment. In fact, I would make several copies of it. So, I'm just going to make a copy and call this 1pi busy. Let's open that up. Give it a minute. There we go. Wait. And now we wait. Oh, okay, there we go. Alright, so this is the busy wait for enforcing mutual exclusion. So, let's begin by adding another flag in here. So this is going to be yet another global variable in flag. We are going to assign this a value of 0 in the main function down here. So I'll just type this in here. Okay, so that just means the first thread that is allowed to enter the critical section is thread 0. In the thread function, which is all the way down here, we're going to add a few bits of code here. While flag that's not equal mind, right? So it isn't really a for loop because we don't have a body for the for loop. No, I mean while loop. It's just the while and then the condition. So it's really gonna repeatedly test this condition over and over and over again until the thread that came before it. So if this is thread n, the thread before it would be thread n minus 1. So, at some point, thread n minus 1 is going to exit its critical section, which I'm going to then code down here. There we go. So, flag plus plus. Also, if the flag variable goes over, if we have 10 threads and this was thread 9, it would then be thread 10, but there's no thread 10, so it just loops back to 0. So that would be flag equals flag mod thread count, because we want this code to work regardless of the number of threads we use. So really, those are the only changes we have to do to make this program work. I'm gonna close the code editor, text editor. I am then gonna open the terminal, so right click, open in terminal. There we go. Let's compile this program. So it is gonna be that long compile command. Here we go. gcc-g-wall-o. The name of the executable, I'll say py-busy. The name of the source code file, I'll say py-busy.c-lpthread. If I press enter and nothing else comes up and I get the prompt again, that should indicate that the okay, there we go. It worked. It was just being a little slow. Alright, now I get to run this thing. So, py-busy. If I just do that, it's gonna do a segmentation fault. That just simply means I did not specify the number of threads or the number of terms. Remember, the code is expecting that I pass in the number of threads to run, followed by the number of terms to add. So let's just fix that up. So /py-busy. Let's do it with one thread and 1 million terms. It works. If I do it again, it still works. If I say that, but with 2 threads instead, it is locked up now. One thing I can do is open up Ubuntu's equivalent of Task Manager. That's the system monitor, and I should be able to see what each CPU is doing. So you see that red line up there? One of the CPUs is at 100% utilization. So this is the problem with a busy wait for our program. Because we are doing that check, flag doesn't equal my rank over and over and over again, the threads, if they are not executing that critical section, they are doing unproductive work. It's just going to slow down the system. And when it slows down like this, the only way to really stop it is to just press Ctrl-C. Let's try it with a more reasonable 100 terms. This is going to produce a very inaccurate result for pi, only accurate to 1 decimal place. Let's try it again with, say, 1,000 terms. We get a slightly better estimate. Maybe 10,000 terms. Maybe 100,000 terms. And here we go. This is the part where this is where it starts to slow down. And, oh, look at that. CPU 5 just shot up in utilization. And so did CPU 2. Yeah. Let's just stop it there. If I go back and do like 4 threads and 100 terms, I still get a good estimate for pi, but let's do like 1,000 terms. Let's do it again. 100,000 terms. Now. Oh! Okay. And just like that, I have 3 different CPUs that have skyrocketed in utilization. They are all doing that flag does not equal my rank check over and over and over again. Let's stop it. So, this technically does work for some situations, but this is not the situation in which you want to use a busy wait. Let's do something else. That something else is a mutex. Short for mutual exclusion. It's a log. It's basically a log. I'm going to make another copy of my pi estimating program. There we go. I'm going to call it pi mutex. Open that up. So pi mutex is going to be yet another variant of our pi estimating program, but instead of using a busy wait as we've seen, which as we've seen results in extremely high CPU utilization for unproductive work, we want a mutex instead. So the code additions for that is, okay, so this is the busy wait. This is the mutex. We still need another global variable that is of type pthread mutex t mutex. This is our mutex lock. We need to initialize that in the main function. So somewhere towards the beginning of your code, we're just gonna initialize lock. Or I should say initialize mutex. So that the function for that is pthread mutex init. Pass in as the first argument the address of the mutex. Pass in as the second argument num. There we go. Now towards the end of the program, add in pthread mutex destroy. We created the lock at the beginning, we destroyed the lock at the end. So, pthread mutex destroy, pass in the address of the mutex. Nothing else after that. There we go. So, this line of code is our critical section. Sum plus equals the right hand side factor such and such. So that's a critical section. So before we enter the critical section, we call pthread mutex lock. So we simply say pthread mutex lock, pass in the address of the mutex. There we go. Acquire the lock before entering the critical section. And then release the lock after you exit the critical section. So, pthread mutex lock, and then pthread mutex unlock. Pass in the address of the mutex. There we go. Alright. I'm going to leave open the system monitor for now, and now I'm just going to clear the console, type ls to see what we have. We have various programs written here already. PyBusy, PyMutex is the one we're going to compile now. So let me just get that command up again. So gcc-g-wall-o. The name of the executable is going to be PyMutex. The name of the source code file is pymutex.c. Press enter, it compiled. ls to see the list of files again. There we go. There's our new program. So let's do /pymutex. And once again, if you type just /pymutex and nothing else, it's gonna segfault because it's expecting us. The program is expecting us to type in the number of threads and the number of terms. So let's do it right this time. Let's do 10 terms and 10,000. Let's do 10 threads and 10,000 terms. We got 3.141923. Do it again. And not only are we not getting any CPU usage spikes, but by doing this over and over again, we see that the estimate for the number of pi is accurate. Well, accurate to like 3 decimal places, but it's going to be more accurate the more terms you add, of course. and you can see this CPU utilization spike as I try it several times. But you should also find that the estimate for pi does not change every time you run it. This begs the question that I mentioned, and that is this giving us a speed up after all? Excuse me. Let's do 1 thread and 100 million terms. So that is 1 and then 8 zeros following it. Get a huge spike in CPU usage, and you get an estimated value for pi, 3.141593. Let's do it again. But now, let's do it again with this. Okay, so it says it took us about a little over 2 seconds for the program to run. Okay, so this is with 1 thread, so no parallelism at all. Okay, so there is still the work of the program. It still must make a new thread and then join back with it, but it's that 1 thread that's doing all the work. If I instead do 2 threads, is it any faster? That ran for 7 seconds. Let's do 4 threads. Eight threads. So, one other caveat I should mention. If you really want to get accurate benchmarks, so you should run the same program multiple times and then take an average. I would probably advise running the same program like a few dozen times, like 30 times if you can. More the merrier. So, but even without doing that, we notice that they're all running about the same amount of time, regardless of the thread count. If I run this again with 8 threads and 100 million terms, it still took about 6 seconds. If I do it again, it still took about 6 seconds. If I do it again, it still took about 6 seconds. Okay. So, we got the program to be parallelized, but it's not running any faster. And that's because of how we wrote this thing. Look at the critical section in the thread function. Notice that it is within a for loop. That means we are accessing the critical section every iteration of the for loop. If we can get the critical section accesses to be lower, we would have less competition over the critical section, which should, in theory, have this program run faster. And there is a way to do that. All we gotta do is modify this program once again. So, you are probably going to want to make another copy of this program. So I'm going to make another copy of this program, call it pi mutex 2. Okay, so this is gonna be the same as the mutex program, except we are gonna modify it. So instead of adding to the global sum, we're gonna add to a local sum. And then after the for loop, we're gonna add that local sum to the global sum. So what I'm gonna do is I'm just gonna copy all that, paste it down here. I'll move it back one indent level, and I'll remove that code for the critical section. In fact, I don't even need this code for lock or unlock within the for loop anymore, because there's gonna be no more critical section here. So for this modification, we're gonna add to a local sum. And we're gonna call it my sum, just to keep with the theme of all of these local variables being prefixed with the word my. Oh yeah, we have to initialize this value. We have to initialize this variable to be value 0, and then we can have it take the place of sum in here. So now this for loop is gonna run, but then so is the for loop that every other thread is gonna run. It's only when we exit the for loop and try to add to the global sum, that's where we get the competition of threads trying to access the same thing. But at this point, every thread only ever has to access the critical section once. What are we gonna have for our critical section? Well, my sum is going to be on the right hand side. On the left hand side is going to be the global sum. So it's just going to be sum plus equals my sum. Save that. And now let's clear the terminal and let's run this program again. So this is called PyMutex2. So let's compile that. There we go. There we go. Let's make sure this program runs, so /pymutex2. And once again, if I just don't type anything after /pymutex2, it's gonna seg fault because it needs the number of threads and the number of terms. Let's do 10 terms and let's do 10 threads and 1 million terms. There we go. Now we have an estimate for pi. So the program should run as it normally does. And if I run it multiple times, we should see that the estimate for pi doesn't change. But does it run any faster now? Let's run this with 1 thread and 100 million terms. And let's add that time command. Okay, so it ran for about 1/3 of a second. If I did it with 2 threads, in theory it should run in roughly half the time. And it more or less does. It ran in roughly half the time. And we do it again, and again, and again. We should see that it runs in roughly half the time. If I do it with 4 threads, now it runs in roughly 1/4 of the time. A little over 1/4. And if I do it with 8 threads, okay, now we are reaching the point of diminishing returns. With 4 threads, it ran in, what is that? Roughly 80 milliseconds, and now it's running in 60 milliseconds. So, right around this point, we are not getting any more speed increases. But that is just due to this virtual machine only having 6 CPU cores. If I got this to run on my main machine, which for reference, is a... If I ran this on my main machine, which is for reference and running an 8-core 16-thread CPU, I would be able to get more performance by maxing out every CPU core I have available. I can't do that because P-threads, I cannot get it to run on a Windows machine. I know there is a way, but for consistency, I'm just gonna show it to you on an Ubuntu virtual machine because it's just easier to work with. In my experience, it was just easier to work with P-threads on a Unix machine. It's gonna get a lot more fun when we get to OpenMP, I promise. Alright, so we are getting a speed up. So, repeatedly running this program over and over and over again and seeing what kind of speed ups we get is eventually going to be the topic, well, the main thing you're going to do for your benchmarking projects. However, we are not done yet. There is still one slight issue with this program. And that is, we impose a constraint in which the thread count must perfectly divide the term count. So if I do by mutex 2 and run this with 10 terms and 10,000, 10 threads and 10,000 terms, I get this estimate for pi. If I run it over and over again, I get the same amount. But what if I ran this with 11 threads? Okay, so it's slightly off again. And that's because this program was not meant, it was not programmed correctly to work with an arbitrary amount of terms and it was not meant to work with an arbitrary number of threads. So as I've shown in the slides, the issue is how this program divides the work. Let's go with a smaller example. So let's say 10,000 terms is a good size amount. What if I do it with 3 threads? And then if I try it again with 4 threads, we are getting some variance. We are getting some variance with our estimated value. So I am going to investigate this by making yet another copy of our program. Let's call it pi mutex 3. Rename. Open a new copy. So we can add a little bit of code just to see what terms our program is adding. And that little bit of code is this. I'm just going to insert it down here, and it is print f, and it's going to be this long print statement. And then for these placeholders, those are going to be my rank, followed by my rank. My last I minus my first I. And then my first I, and then my last I. There we go. So some thread is going to add some number of terms from starting index to stopping index. Let's run this program now. So this is pi mutex 2. We now have pi mutex 3. Oops, wrong file name. Okay, so there is a slight mismatch, and this should be %LD, not LLD. My bad. Well, easy fix. Clear. Try that again. There we go. Now if I run this new program, pi mutex 3, I need to specify the thread count and the term count. We previously were running the last program with what? Three threads and 10,000 terms. There we go. So thread 0 is adding 3,333 terms from indices 0 to 3333. Thread 1 is adding 3333 terms. Thread 2 is adding 3333 terms. If we add those up, that is 9,999, which is one term short. And because this all starts from 0, this is basically terms whose indices are 0 to 9,998, and term 9,999 is missing. If I did this with 4 threads, now each thread is adding 2,500 terms each. That perfectly adds up to 10,000. So the issue is with how we are dividing our work. The easiest fix to this, well, actually there are 2 fixes, as I mentioned in the last video. And either one will work. So each thread is going to add some number of terms. But as we saw in here, if the number of threads does not evenly divide the number of terms, we are going to get some terms missing, whose quantity is determined by the remainder of the term count divided by the thread count. So if thread 0 adds 3333 terms, thread 1 adds 3333 terms, and thread 2 adds 3333 terms, why don't we just force that last thread to add the missing terms? And that is one way we can fix this problem. In fact, let's do it right now because that requires the least amount of coding. So if this is the last thread, overwrite my last I to be n. Because if thread 2 is adding terms 6666 to 9999, but we wanted to add terms 6666 to 10,000, though keeping in mind that it's going to add everything but that last term, so it's technically going to add terms 6666 to 9998, and we wanted to add terms 6666 to 9999. We have to force thread 2 to have its my last n to be 10,000. So, how do we know that this is the last thread in our group of threads? Well, we have a rank that determines each thread's number. If we compare that to the thread count, we can easily determine which thread is which. So, if my rank plus 1 equals thread count, my last I equals n. There we go. So this is bug fix number 1. You can use either bug fix you want, either one will work. So if we bug fix this program and run this now, what we should find is if I run this program with 3 threads, okay. Did it compile this time? Okay, let's try it again. Just make sure. Okay. Okay, the issue is that I had this print code before the bug fix. So I rearranged the lines of code so that the bug fix occurs before the print line, and then recompile it. It should work as intended. Well, it was already working as intended. It's just that the code was executing in the wrong order, which is ultimately what we're trying to fix here. So if I run this with 10,000 terms and 4 threads, I get this estimate for pi. But if I do it again with 3 terms, I get the same estimate for pi, because the last thread, if there are any terms that are in danger of going missing, the last thread just adds them back. I can do this again with 7 threads, because 7 does not evenly divide 10,000. Can I say that this program is load balanced if thread 6 here has to add 4 extra terms? Well, it's load balanced enough. It's close enough that this is for our purposes close enough. But the point is, regardless of the thread count, we should have the program run and give us the same answer every single time. In other words, it works. The program works. Hey, you want to see the other bug? You want to see the alternate bug fix? You know, I'm going to show it to you anyway. So, in the instructions for the programming assignment, I showed part 1, and then 2, and then 3, and then 4. You only need to implement one of the 2 fixes. You do not need to do both. In fact, if you somehow implemented both, you'd somehow have to rewrite, like... The thing is, there are 2 separate fixes, and you only have to implement one. If you try to implement both, they'll just conflict with one another. So here is the alternate fix. So this is option number 2. In the instructions, it was labeled option 1 and option 2. So I'm actually going to delete all of that. And I'm actually going to delete all of this. So option number 2 does away with my n, my first I, and my last I. It also means that this for loop is not going to work properly. Not until we rewrite it. So, as I explained in the slides, we don't need a my first I, and we don't need a my last I. But we can just write the for loop as we normally would. Well, in fact, let's start with that. So, for int, well, log long I equals 0, I is less than the number of terms, which is n, I plus plus. Okay, that's our starting point. But this is code that is going to be executed on every thread. So we need to give each thread its own starting point. So in a way, we still need my first I. But we get it for free from the rank. So on the right hand side of this assignment operation, my rank. Oh, and we cannot increment by 1 anymore. It has to be incrementing by the thread count. So the thread count is all the way up here. So I equals my rank, I is less than n, I plus equals thread count. So this fundamentally changes how this program works. And to demonstrate that, I am going to leave it incomplete and try to compile and run the program. Oh, right. This code no longer works anymore. So I'm just going to delete that too. So this program works fundamentally different from the last or the previous implementation, and I'll show you. I'll set the factor to 1 for now. And then I'll run the program as you normally would. So that is pi mutex 3, 10 threads, 10,000 terms. So the estimated value of pi is 22. What the heck happened? Well, the problem is, in the increment step of the for loop was also the step for flipping the sign of factor. But the problem is with this code here, if my first I mod 2 equals 0, factor equals 1, else factor equals negative 1. Let's add back the part of the code that flips the sign of factor, so factor equals negative factor. So this is the sign flipping operation, but we don't have a my first I anymore. But we do have my rank. So my rank simply determines the index of that thread's starting position. It's either going to be even or odd. So, is this fix enough to get that sign flipping behavior we expect to see with this sum here? Not quite. Not quite. So this does not quite work. So instead, I'm actually gonna put this code within the for loop, and I'll write it in like this. If I mod 2 equals 0, factor equals 1.0, else factor equals negative 1.0. So all of that is sign flipping code for the factor. I can remove that from the increment step of our for loop here. I can remove the assignment operation up here, and hopefully this will work now. Let's try it. There we go. And if I do it with 1 thread, we should still get the same answer. If I do it with 100 threads, I should still get the same answer. If I do it with 68 threads, because the average of the 67 meme and the 69 meme is 68, it should still work. The program works. Alright, so that's going to be it for this video outlining what to do for the programming assignment 2. So this is Pthreads programming assignment 2. Part 1 was implement a busy wait and see how far you can get before you have to press Ctrl-C. Part 2 is rewriting it with the mutex logic. Part 3 is rewriting it, but you optimize it so you instead have a local sum that you then add to a global sum. And part 4 is rewriting the code once again so it works with an arbitrary number of threads. So yeah, that's your whole programming assignment. So this is programming assignment 2. We will be revisiting this program for when we get to benchmarking, which might be a topic for potentially this week. Alright, so that's going to be it for this video. See how far you can get with the instructions, and I'll see you in the next video. Bye.